So now we're going to talk about reactions involving gases. We've done stoichiometry with masses of things and with solutions. We can also do stoichiometry problems with gases. So we can use the ideal gas law to figure out the amount of moles of the gas, whether it's a reactant or a product. Because remember, stoichiometry, the general idea is we've got grams to moles to moles to grams. The clue there, or the secret thing there, is there's always moles in the middle. So with gases, instead of starting with a mass, we may start with a volume of a gas. And we have to know its temperature and pressure, but we can use the ideal gas law to find the moles. And then moles of other thing would be the mole ratio from the balanced chemical equation. And then at the end, we could be finding the mass of a solid, we could be finding the volume or the concentration of a solution, or we could find the volume of another gas. So if the reaction is occurring at STP, things are much simpler, because then we can use 22.4 liters is equal to 1 mole of gas. And that ends up working just like a molar mass does for solids, except the extra convenient thing is it's the same number no matter what the gas is. So if you see STP, have a little celebration inside and use 22.4. So this is our regular grams to moles to moles to grams. With gases, we need to know pressure, volume, and temperature of the gas, so we can convert to moles of the other gas, and then to pressure, volume, temperature of the second gas. The pressures here might be total pressures. They could also be partial pressures. So let's do an example. In the following reaction, 4.58 liters of oxygen was formed at pressure equals 745 millimeters of mercury and temperature equals 308 Kelvin. How many grams of silver oxide decomposed? So this is a stoichiometry problem. I have a chemical reaction occurring. And so I'm going to use the balanced chemical equation to help organize my information. I've got an amount of oxygen gas. So under O2, I'm going to write 4.58 liters. That's the volume of the gas. And then I'm given a pressure and a temperature, and those also relate to the oxygen. So pressure equals 745 millimeters of mercury, and temperature equals 308 Kelvin. And then I look at the question, how many grams of Ag2O? So I'm looking for the grams of this thing over here. Okay? So with my regular starting point of grams to moles to grams, I am finding grams at the end, but I'm not starting out with a mass of gas. So instead of grams of oxygen, I've got liters of oxygen, and I know the pressure and the temperature. Using that and the ideal gas law, I can find the moles. Moles of O2, and stoichiometry, I have a 2-to-1 ratio. I can find moles of Ag2O. And then molar mass allows me to find grams of Ag2O. Any questions? This is the hard part, figuring out what we're going to do, making the plan. Now we just need to follow the plan. So the first thing I need to do is convert liters of oxygen to moles of oxygen. So instead of looking like dimensional analysis, this part is using the ideal gas law, the equation. So I have volume. Let's go ahead and label that volume, pressure, and temperature. I'm going to use the ideal gas law. The moles of gas is the pressure times the volume divided by R and T. So the pressure is 745 millimeters of mercury. Is that going to work in the ideal gas law? No, I need atmospheres. So there's 1 atmosphere for every 760 millimeters of mercury. So that's 0.98026 atmospheres. So that was a little side conversion. A conversion diversion. They gave me the volume in liters, so that's convenient, 4.58 liters. Down here I've got my ideal gas constant. And the temperature, they gave it to me in Kelvin, so that was nice of them. Again, here we're dividing by 2 different numbers, and so you need to make sure that you're communicating with your calculator correctly. If you want to multiply by those things in the denominator, you need to use parentheses. I'm coming up with 0.17763 moles of oxygen. Anybody else do the calculation and get that number? Thank you. So now I've gotten to moles of oxygen. I'm going to go to moles of the silver oxide. And then to grams of the silver oxide. So moles come down here. And not grams, moles of oxygen. Most of these stoichiometry problems are variations on a theme. So here's my moles in the middle, my mole ratio, 2 moles of Ag2O for every 1 mole of oxygen, so those numbers go in there. Grams to moles, that's my molar mass, which I have to calculate. Silver 107.9. $231.8. 231.8. Yeah, I did. 231.8. It's a talent to say one thing and write another. I still don't know how I managed to do that. 231.8 grams per mole. So now I take my moles, 17763 times 2 times 231.8, 41.175 grams, 41.2 grams. You got something else?
Did you divide by 2?
I forgot the 2. I forgot the 2.
Yeah, it's 82.
Yeah. And that's why we do things twice. Maybe I'll be in the clear for the rest of the day. Have I made my mistakes for the day already? Probably not. Is that better? Any questions? $82.3. Came up with 82.4. Depends on how you round things. Close enough. Let's do another one. How many liters of oxygen at STP are required to form 10.5 grams of H2O? So we've got the magic at STP. That means we can use the molar volume of a gas. 22.4 liters is equal to 1 mole. You can use the ideal gas law, but molar volume is a lot faster. How many liters of oxygen are required to form 10.5 grams of H2O? So I want to make 10.5 grams of H2O, and I want to know how many liters of oxygen do I need? So grams to moles to moles to grams. I am going to end up with grams of H2O, moles of H2O, and I'm starting with oxygen. But instead of grams, I'm starting with liters of oxygen. Questions?
Can you just compare this to moles in this case?
Well, I don't have the, you see what I did? I did the whole thing backwards. I did this whole thing backwards.
Oh,
Yeah. Let's try that again.
maybe now you be.
Yeah, it's like there's a reason it wasn't making any sense, because there's my second big mistake for the day. What are we starting with? We're starting with H2O. Grams of H2O. I don't know why, I just did it completely backwards. We get to the end, and we're asked for liters instead of grams. So instead of grams, we're going to find liters of O2. Okay. Is that better? Yeah. Sorry about that. I wish I could say I did that to see if you're paying attention, but that's not the case. Okay, so we have grams of water, 10.5 grams of H2O, and I'm going to go to moles of H2O, and then I'm going to go to moles of O2, and I'm going to go to liters of O2. If you can clearly see this path in your mind, you don't have to write it down. But most students at this point in the semester, you need to write that down, okay? Write it down, then you've got a roadmap to follow. You can write this out, and things will go so much more smoothly. And this stoichiometry business is one of the main reasons that I think you really, really need to understand dimensional analysis. Because if you understand dimensional analysis, this actually falls together very easily. So now I look for my numbers after I have my units in. Grams per mole for water, that's the molar mass of oxygen, and hydrogen times 2, so the molar mass of water. Mole ratio, I've got 1 mole of oxygen for 2 moles of water. 1 mole of oxygen for 2 moles of water. And this last part, because it's at STP, I can use 22.4. 22.4 liters per mole. .5275 liters. 6.53 liters. .53 liters. Any questions? There's an endless variety of stoichiometry problems. So you can't just learn a set of equations and, oh, it's this one, I do this. You have to be able to think about it and put it together.